Reason we ignore constants and non-dominant terms is, for example, this is the curve for the time complexity n square. N square means quadratic time complexity. So this is 3n, this time complexity is 3n square plus n plus 1, right? So it is more number of operations than n square does, because due to this multiplication and addition, this time complexity will have more number of operations than n square, right? So that is why the curve will be little more up. This time complexity is 3n square plus n plus 1. The next worst time complexity than n square is cubic time complexity. Think that n cube is worst time complexity than n square. And the better time complexity than n square is n log n, big of n log n. So here my point is, by adding these constants like 3 and lower order terms and constants, this curve, the difference between these two curves is just this multiplication 3. For example, it does 10 operations into 3, it is 30 operations will do this time complexity, but this curve will never come to this point. This multiplication and this addition will never add new powers to n square to reach here to here. To reach from n square to n cube, we need infinity number of operations as to be increased for the n square. So it will never happen infinity operations by adding these constants and lower order terms. That is why these are less important when we compare with number of operations infinity. This is the diagram I'm trying to draw there. So let me explain you here. So the difference between n square and n cube is infinity. To reach from here to here, we need infinity number of operations. These constants like 3 plus n plus 1 will never add infinity number of operations. Of course, there is slight difference between these two curves, but it is never equal to n cube time complexity. That is why we ignore these non-significant terms like constants and lower order terms. The next point is the current time complexity is n square. So to reach to its lowest time complexity, the gap between them 0. From current time complexity to upper time complexity, the gap is infinity. From here to here, the gap is 0. So these constants will never add power. Let me prove this difference is infinity, 0 and constant mathematically by using limits. See here I'm using limits. Here limit will help us to find how fn is behaving compared to g of n. Here fn we take one time complexity, g of n we take another time complexity which we want to compare against. For example, I want to compare these two. So take phi n square as f of n square as g of n. So this limit will help us how phi n square is behaving with the n square time complexity when n growing to infinity. So this is the use of infinity with the limits. So f of n one time complexity and g of n is another time complexity. So by using this limit, we can find that is f of n growing slower or faster or same way. In the same growth, fn is growing with the g of n. This we can find out by using this limit. Here, first I'm trying to prove this infinity here. So the infinity is the difference between n square and n cube, right? So here I'm taking f of n as n cube, g of n as n square. So the result should be infinity, right? F of n, g of n, n cube, n square. So if you cancel n square out of n3, the result is n. If you substitute n with the infinity, so this n will become infinity. Difference between these two time complexities, infinity number of operations. Okay, so this one is completed. So as result is infinity, it means that f of n means n cube is grows faster than g of n, faster than n square. So f of n cube belongs to other time complexity class. It is higher time complexity class. As a result is infinity. The next I'm trying to prove here is the difference between n square and n log n is 0. I'm taking n log n as f of n, g of n as n square. Here n I'm cancelling one time here, n log n by n. So when I substitute n with the infinity, log of infinity infinity. So anything by infinity is 0. Since the result is 0, f of n grows slower than g of n. So here n log n growing very slowly compared to n square. So this n log n belongs to lower time complexity class. That is why I declared it as a n log n time complexity, this curve. So the next comparison is this constant phi. I'm taking example time complexity as here phi n square plus 2n. So this has f of n, and next one is the g of n. F of n, g of n. Here one time, here two times n square. So the result is 2 by n. Anything by phi plus 2 by infinity. Anything by infinity is 0, right? So the result is phi here. So the difference between these two curves is just constant. Here infinity means the difference between n square and n cube time complexities. For n square, whatever the constants you multiplied with n square, it will never reach to n cube because the gap between our number of operations difference is infinity. The next phi n square, see phi n square will have more number of operations than n square, but it doesn't mean that as many as operations as n cube does. This is very important point. Here phi n square, if you consider phi n square or some other constant 3n square, 2n square, if you consider every time complexity as separate complexity class, it is very difficult to define every possible constant factor with different complexity category. For example, tomorrow 2n square, 3n square, 5n square, 6n square, every constant with some time complexity we cannot define a separate time complexity category, right? So it will be very impractical. So this would make complexity analysis impractical because actual order or growth remains same. Here the actual growth is same between these two. This constant factor, it is very minimal compared to infinity. That is why the growth rate between these two is same. Growth rate means they comes under same time complexity. That is why we group all functions with the same fundamental growth into single class. That is why this all comes under n square time complexity. Functions with the same dominant term belongs to same complexity class.